Now let's talk about how to find the admittance on a Smith chart. I'm going to begin with the example where ZL was 50 plus J50 on a 50 ohm transmission line. So it was 1 plus J1, which we plotted right here on the Smith chart. This was ZL. If I want to find YL, that is 1 over ZL. The way we find that is called translating through the center of the Smith chart. You take your straight edge and you draw a line from the center through your point and you continue it on here. So it's one straight line right through there, right through the center of the Smith chart. And then you mark your distance, like so, and you copy that distance right here, starting at the center, going to this point right there. This is YL, so you can say it's translating through the center of the Smith chart to the point YL. Let's read the value of YL. YL has a real part of about 0.5, and it has an imaginary part which is negative. Remember, down here we have the negative imaginary part. Read it right out here. Has a negative J 0.5. If we wanted to know the admittance in mhos, we would have to denormalize. So in order to find YL in mhos, we're going to take YL on the Smith chart and we're going to multiply it by Y naught. Y naught is 1 over Z naught, so it's 1 over 50. So YL is going to be equal to 0.5 minus J 0.5, and then we need to multiply by 1 divided by 50, and that's going to give us the value in mhos. And that's equal to 0.01 minus J 0.01 mhos. That's our YL. Now, let's also talk about some very special cases. We're going to consider an open circuit and a short circuit because those are very important. We use them for building things, and also many of our devices end up acting like high or low impedances close to an open circuit or a short circuit. So for an open, we know that the impedance of an open circuit is equal to infinity. So let's find where the real part becomes very, very big. Here's the real part of 1. Here's the real part of 2, 50, and so on. Right here is where we have the impedance of an open circuit. The impedance of a short circuit is 0. So where is our real part 0 and also our imaginary part 0? Our real part is 0 every place on the outside of the Smith chart. So this circle right there is where the real part is 0. The imaginary part is 0 right along this axis. So that point right there is Z of a short circuit. Now how about the admittance of an open or a short? Remember, if we wanted to find the admittance, we simply translate through the center of the Smith chart. Let's do the short circuit first. We're just going to translate that through the center of the Smith chart right over to here. So this is the admittance of a short circuit. Let's do the same thing with the open circuit, and this is the admittance of an open circuit. Let's also read the reflection coefficient. So the reflection coefficient of an open circuit, we know that ought to be 1. Let's check ourselves. So right here is the point where I have the Z of the open circuit, and that's where I'm going to find the reflection coefficient. Its phase is 0, just as we expect, and its magnitude, if you take these 2 points, put them on your piece of paper, and mark them down here, its magnitude is 1. How about the reflection coefficient of the short circuit? We know that it should be minus 1. So here's the point where we're going to consider the short circuit. Let's come over here and measure the phase, which is 180 degrees. And then let's bring this magnitude right there down here to the center, and it has a magnitude of 1 and a phase of 180 degrees, which is minus 1. Let me make a note here that when finding the reflection coefficient, use the impedance points. Do not use the y points in order to find your reflection coefficient.